Can people on Zoom hear me? Hello? Hello? Anyone on Zoom? Can anyone on Zoom hear me? Sounds good. All right. Those things in the back, is this readable? You can see this. All right. Good afternoon. How's everyone doing? Doing well? How are people feeling today? Good, bad, meh? Few thumbs up? Yeah. Let's see what's coming up over the next few days. Project 2A is going to be due this Wednesday. How are people doing on that? Doing well? Yeah. Kind of between. All right. Just out of curiosity, how many people are done with 2A already? How many people still need to work on it? Anyone haven't started yet? No. Start early, please. Yes. All right. Other than that, we have Lab 7 that's due this Friday. And that should be the main assignments for the week. Before we get started, does anyone have any questions? All right. In that case, let's get started. All right. So Friday we covered the hash set hash map idea, where we use a hash table to kind of store items according to their hash code. So we take an item. So we take an item. We use its personalized hash code function to turn it into an integer. We take its number mod some amount, and we store it in a bucket corresponding to that. And the idea is as long as the number of buckets we have is about the same as the number of items we have, on average, will take only a constant amount of time to find an item. That's kind of how we built our hash set or our hash map. We also showed that we could build it using a tree, assuming things were comparable, and that would take a logarithmic time. So here's kind of a recap of what we discussed on Friday. So assuming our hash code works nicely, on average, things are going to be constant runtime. So today, kind of what we're going to be doing is we're going to be seeing kind of the concerns that we might have with using a hash table for this, right? We have a bunch of like these stars and asterisks on here that these are constant time. Uh, in practice, there are some cases where you're not going to get constant time runtime, and we're going to just show what those bad cases are. So let's just play around to kind of get a sense of how a hash table would work. Here I'm going to be using a hash visualizer, and we'll have 20 items starting with 6 buckets. And I'm going to start with a resize factor of 10. That just means that I'm basically disabling resizing. We'll never resize until the number of elements is 10 times the number of buckets, which in this case will never happen. So if we run this, we'll kind of see these items. So for context, these are numbers. We're giving each a color. And we're going to say that two things with the same number are equal, even if they have different colors. So if we run this, we get this pattern. Does anyone notice any patterns with this? Or what do you notice about this result? Yeah? Yeah, there's a lot in 3 and 0, not a lot in 4 and 5. I wonder what happens if I just run this a second time. It might just be random chance, right? Is this the same thing? All right. Yeah, the Java system tends to like the same thing sometimes. There's no real good reason why that's the case. But like, yeah, if you just play around with this, then you do get this kind of pattern. It kind of really depends on the system that you're running on. Uh, Here's, for example, another version of when I think Josh ran it on his computer. So it is actually slightly dependent on the computer. Anyway, so why do you think we get this kind of distribution? It's seemingly random. There are some patterns that we might see, but I'm not sure if those are due to random chance or due to just or due to like something internally. Why do you think this ends up displaying like this? Modular arithmetic patterns. Modular arithmetic patterns. That's an interesting idea. There aren't really any patterns with modular arithmetic. If you have a random sequence of numbers and you take the modular arithmetic, you should get random numbers approximately evenly distributed. Yeah. Input sequence is not random. The input sequence is not random. Yes. This code, what it is doing is it's putting the numbers 0 through 19 in order, but it's using the default hash code. And the default hash code doesn't actually use anything about the objects themselves. In fact, the default hash code uses the memory address, which is effectively random or should be effectively random. Yeah. Yeah. Yeah, the hash function itself is kind of the weird point here. When we run this code, the hash function itself is deciding where each item goes. It decides a number. And it is effectively just associated with the memory address. I'm not entirely sure why it is that the 0 bucket and 3 bucket end up having a lot of items in them. I think it's just kind of just a random chance. But the specific reason why every single time I run this, it gets the exact same memory addresses is kind of because there's like a Java virtual machine running internally. It's kind of mimicking the behavior of an actual program. In practice, you might get different results if you run this code on your computer. I might get different results each time I like close and reopen my computer. Normally there's like two patterns that it kind of oscillates between, but for some reason today it's only liking this one pattern. I'm not entirely sure what's going on. But in effect, these hash codes, they are effectively random. Here are the actual hash code values that it's working on, and these are just the numerical values of the memory addresses. Like this number 0 is stored at location 513,169,028 in my computer. Now, let's say that let's say that I decide to override the hash code function to return 0 only. What do you think is going to happen to the distribution? Any suggestions? Yep. They're all going to go into the 0 bucket? Yeah, that seems like a reasonable statement to make. Let's take a look. Here's my colored number class, and I'm just going to uncomment out this. So now the hash code has been overridden to return 0 always. And if I run my hash table visualizer again, yeah, now everything is stored in 0, and it's so big it goes out of the out of screen. Is this good? No. Why is this bad? Yeah. Yeah, the runtime's going to become linear. If I want to find 19, it's going to take forever to find it because it's all the way at the very end of this list. So let's try a different hash code. What kind of hash code might I use to get this distribution on the right? This seems like a fairly good, evenly distributed one. Uh, how do you think I got this? Yeah.
Pick the number in the box mod 6.
Number mod 6?
A random number generator?
Random number generator? Well, it seems like every item is in the box corresponding to the number mod 6, as you mentioned. Yeah. If it was random number generator, it would evenly distribute, but there are problems with using random number generator that I'll talk about in a bit. Yeah. Yeah, if you just return the number as a hash code, then the hash table itself is going to deal with the modular arithmetic. So I would say that returning the number itself is probably the more natural approach for this one. Because number mod 6 is kind of weird. I didn't pick 6 specifically. That's more the hash table who does that. So yeah, let's just do that. I'm going to replace the hash code. And instead of doing this, it's going to return, what is the variable name? Num. Num. There it is. And if I run this, then yeah, it looks like it ends up storing things in order like this. Is this a good hash code? Yeah, feels like it evenly distributes things. So we can try out other hash codes that you might want. Any other hash codes you want to play around with? Yeah. Color? Interesting choice. Let's try it out. Let's see. How do I get a colors hash code? The RGB value would be nice. Yeah, I can't just do return color because color is not an integer. I could try to get the RGB value, but that's going to be complicated because I don't know what this color type is. This is something Josh wrote, and I don't know what it is. Someone mentioned I could probably just do color.hashcode. See what happens. Let's see if this works. Seems like it worked, kind of. What was the issue here? Yeah.
After and then the number of the number of options distributed so it would be frustrating.
Yeah. There's only like 4 or 5 different colors that I picked on this thing. They're not too random. And also, as it turns out, we got really unlucky. Blue and white had the same hash code, and yellow and green had the same hash code. So it ends up only using 3 of these bins. Yeah. This isn't quite a good one. Although you can kind of see here's the resulting hash code values, if you're curious. Yeah. FFFF, the white one, was hash code -1 for some reason. Yeah.
Does this visualization resize?
Does this virtualization resize? It does, but I've currently disabled it by setting the resize factor so large that it will never resize. If I set this resize factor to, I don't know, 1.5, then it should resize after, there it is. Yeah, so it does resize after a bit. So we did take a look at these hash functions. And generally speaking, at least for the purpose of this course, the main advantage that we get from a hash function is how evenly spread the numbers are, how randomly distributed the numbers are. Yeah. Do we care about collisions yet? We do care about collisions in the sense that we don't want to have something that has too many collisions, but we aren't looking for cryptographically secure hashes here. You're thinking kind of like hash functions should be hard to find 2 items that have the same hash code. That's not something we need to consider at this point because we don't need that for our hash tables. That is something useful in future classes, though.
Sorry, if the hash code relies on the memory address, then you restart your computer. Does it mean that you'll lose a hash table every time like that the memory address is changed?
Yeah, if it's dependent on memory address, then that does mean that the items are going to be moving around each time you rerun the code. That's actually allowed by Java's specifications because once you restart the program, the entire hash table should, in theory, have been dissolved, right? You don't have things that persist through like various function calls. That does mean that it's not very easy to like store a hash table in a file somewhere and then restore it back. You need to kind of create it anew in memory each time. Yeah. So we did mention that the goal of this function is to spread things out evenly. For the purpose of this class, that's the main goal that we'll be looking at. So we don't need to worry about collisions and things like that as much. So no spread at all would be like returning 0. That was a very, very bad hash function because everything just got stuck in the same bin. We weren't able to get too good spread by choosing color. Uh, so that I would call a bad spread because we only have like 5 different values, even if we expanded it to a really large hash table size. Good spread seemed to be just returning the number itself because that was fairly evenly distributed. What do you think the spread of the default hash code is going to be, which just returns the memory address? Um, how many people say there's going to be no spread? Everything just stays in the same bit. Bad spread, it kind of prefers some items over others. Yeah, kinda. How many people think it's a good spread? Feels like it's about evenly distributed. Seems like a lot of people are saying it's a good spread. Yeah, I would say the same. The memory address is effectively random. There are some patterns that you see, but it's effectively random. We have no control over it. It feels evenly distributed enough. Here's another question. If the default hash code is so good, why do we need to update it with our own custom hash functions? Feel free to discuss with your neighbor for a few minutes.
Um,
Talk with neighbors. Talk with neighbors. All right. Let's bring everyone back. All right. All right. So what do people say? Why do you think we need custom hash functions at all? Yeah.
Might benefit, like in this case, when we store a value, like a number value, we can reach that and it gives us better spread.
Some types of objects might have better spread if we use a custom one.
Like there's type of like characteristic or this type of value inside of it that we can help promote better spread if we return that or we like with different characteristics of an object or different sort of values. And then we can also do kind of keeps the system a little bit is it can every time we construct a new variable or a new object, we can store that we can store a random number that becomes its hash value, right? And then kind of keeps the premise, but ish, but yeah.
All right. Yeah. If you do want to do a random number at each time, the memory address is probably good enough for that purpose because the memory address is kind of random. But yeah, maybe depending on the items you have, you're going to have different properties that you want to focus on. Is there any reason why it's just absolutely not a good idea to use the default hash code? Yeah.
You don't know what it would do to like field value.
We don't know what it would do to field's values. Well, the default one just doesn't do anything to any values. It just looks at the memory address. So that one's safe to use if you are concerned about that. Any other concerns?
Objects that are in like consecutive memory blocks that are of a size that would kind of put them all in the same bin.
Objects in consecutive memory addresses might end up in the same bin. That might be a concern, but I don't think that's the biggest reason. Let's take a look. One thing that I want to note is that in a set, you should only have one item of each type, right? A set is meant to be a set of unique items, and we define uniqueness according to the equals operator. The equals method dictates whether two things are considered the same thing. So let's say that I've set up this method, right? And I have this equals method that just checks if two numbers are the same. It doesn't care about the color. It just checks if the two numbers are the same. And what I'm going to do is I'm going to restore the default hash code right now. This time, instead of choosing the numbers 1 through 20, what I'm going to do is I'm going to add the number 0 repeatedly. What do you think is going to happen here? Let's take a look. What's going on here? Yeah. Okay. Yeah. Yeah, each 0 has a different memory location. So even though we only wanted one 0 to exist in this entire set, it kept adding zeros to different memory locations or to different hash buckets. So here's another example here, right? Imagine that I just take this hash set and I just put in the numbers 12 repeatedly. If I want to check if 12 is contained within this, like this, then I'm not going to be able to find it. Even if I put in 20 times the number, oops. Even if I put in the number 12 20 times, I have 12 different 20s inside my hash set. This is the actual hash set that's used in Java. And I still can't figure out if 20 is in here. It claims that I put in 20 12s, distinct 12s in it, and that 12 is not contained in here because the memory addresses are different. In fact, I could add in 20,000 12s. And nope, it still can't find the 12 because the memory addresses are different. So we would expect this to return true, right? 12s are all the same. If we put in 112, we should have only 112 in the hash set. And the 12 should return true because it's in there. But if we use the default hash function, it is not going to return true. It is going to return false. And in this case, if we assume we only have 6 bins, it's going to return false with 5/6 probability. Why is there a chance that it might return true? Yeah. Yeah. There's a slight chance that you get really lucky and the 12 that you create new and the 12 that you used to have happen to be in the same bin. In that case, we'll get the right answer. We'll find the 12. But if not, then we're looking at the wrong bin every single time we're trying to put the item in. So because of this, the default hash code is not going to work nicely with this. What do we need to do to change this? Yeah? Converting to a reference type? Color number is already a reference type. The references being different from the equals values is the reason why we had issues. Hash code customized, so it can be like reproducible. Yeah. One approach is we can just update the hash code method, right? This is kind of the reason why we need the hash code method to be overridden. If we have something that's dependent on the number like this, then the hash table should work fine. If I run the hash set here, after I run 20,000 items, I should have one item in the hash set, yes, and that returns true. I was able to find the item that I put in. If you want to look at the kind of the visualizer version of this, here's how it'll look, right? The 0 is found in here. It'll get stored and we'll always see the 0. There's only one 0 in this, no matter how many times it increases. I think there's a bug in the visualizer which just adds bins, even if there's only one unique item in here. But other than that, it'll work. Yeah. Explain why, like in the old example, you can still get a true. In the old example, you can still get a true. Well, kind of the reason why is, imagine that I don't have this, right? And I just run this. There's still some bins with zeros in them, right? If I look for 0, then I'm going to get a true if the 0 happens to be in the bin that I look for. But if you're in that bin, you should check contains by equal. They have different memory addresses. If you're in the bin, you should check by equals. In a hash set, we consider two things to be the same when they're dot equals each other. So the way that a hash set will actually work is it'll use the hash code to find the bin, and then it'll look in that bin to see if anything is dot equals the item, right? We don't want to use equals at any point in our hash set because we want to ensure that even if two things have different memory addresses, if they are equal by dot equals, they are considered the same thing. Define the equals function. Yeah, we define the equals function here to only be like if the num is the same. Yeah.
It's called also particular color or particular like the memory address being assigned to a particular bin.
How is the particular color or memory address assigned to a particular bin? Modular arithmetic. So we take the memory address, we take it mod 6 in this case, and that's the bin that the item goes in. The color has a hash code method of itself. I believe it's just the numerical value of it. Because if you look at what a color actually is, it's just a 32-bit number between 0 and 4 billion. Uh, so I think it's just that number for the hash code for that. Yeah. Where did my So in effect, if we override the equals method to say multiple things are equal, then we need to also override the hash code method to ensure that if two things are considered equal, then they need to have the same hash code. Otherwise, hash sets just don't work properly. If you set things up where the hash code returns unequal items for two things that are considered equal, then there's a chance that those items go into separate bins on the hash set, and you're unable to find the two. Yeah.
So, so, so because like two objects, like, is there, wait, the default hash code is based on memory?
Yes, the default hash code is just based off memory address. And if two things have the different memory addresses, but are considered equal to each other, then they'll end up having different default hash codes. Yeah. Similar to a virtual page in OS development. I guess in a way you can think of it like that. In a way, virtual page memory systems are kind of similar to hash tables because you're assigning uh, like physical pages to virtual pages, key to values. You can say that. I guess there are some slight distinctions because you don't normally have multiple virtual pages assigned to the same physical page unless you're dealing with like multi-threading things. But that is an interesting parallel. I will say it's entirely out of scope. You don't need to worry about what I'm talking about until 61C. Yeah. Now, just as kind of a quick check, let's say that we have the same equals method, but we don't override hash code like this. What will happen when we call the add zero? Uh, which of the following can happen? Feel free to discuss. I'll come back in a minute. This thing flickering behind me. Is it flickering behind me? Just every now and then? Why is this flickering? I don't know. All right. Let's bring everyone back. What do people think? How many people say zero A is possible? It's possible to get another zero in bin zero. Some people. How many people say B is possible? It's possible to get another zero in bin one. I think one person. How about C? We add zero to another bin. Seems very possible. How about D? We don't get a duplicate zero. Few people. All right, let's take a look. If the zero is going to have a different memory address, and it's going to be effectively in a random spot. So if it ends up in hash bin zero, there's no zeros in here, so it's going to add itself there. That's possible. If it's in any other bin, like 2 through 5, same thing. it's going to add itself there. If it's in bin 1, it'll look through the items, it'll see that 0 is already in there and realize that it doesn't need to add anything. So therefore, it's not going to actually add anything there. Because of that, we're not going to get a duplicate 0 at all in that case. So A, C, and D are going to be possible here. So there's a 5/6 chance that we're going to get a duplicate, and a 1/6 chance that we get lucky, equals blocks it, and we end up with only 1 0 total. So in effect, if you override equals, you need to override hash code. Otherwise, contains is going to break, and add is going to result in duplicates with a decent probability. There's a chance that it gets lucky, and it finds the items. But you shouldn't trust that. Any questions up to here? Yeah.
So can we do something like making num an integer, like the container class, and then drawing hash code on that?
Can we do something like making num a container class?
Yeah, well, it's capital I integer instead of lowercase.
I think that'll end up being the same thing. Integer.hashcode is just returning the number itself as well. Yeah. But you could do that. It just doesn't do anything different.
Would all Java objects classes have their own customized hash code function?
Do all Java objects have their customized hash code? Well, anything that changes equals will. Not necessarily anything else. Generally speaking, I think there may be some things which you're not supposed to check if they're equal, which will have the default hash code, but I don't know entirely. In general, you can assume that if Java utils built a equals method that's overridden, then it will also override hash code to be consistent. Yeah. Sorry, I can't quite hear you. If I have two variables that are equal, will they return the same hash code? Is that what you're saying? If I run the program a second time? Yeah. So if you run the program a second time, you can get different hash values. We saw that with memory addresses, they change each time you run the code, except I was unlucky today. So you are going to get different results each time you run the object. But that's fine with a hash code function. It's fine to have different values each time you run the code. The specific language that's used in the Java documentation is that you're allowed to change things each. It needs to be consistent within the same run of the program. There is actually one more caveat that we'll get to in a bit. Yeah.
So wait, why is it bad? Why is it bad if two objects have equal values? Why is the hash set one put them in the same bucket?
Why is it bad if two objects with the same hash code or two objects that are equal but different hash codes end up in the same bucket? I would argue that that's good. We want to have only one of each item in our hash set. And if we're lucky, we end up getting that if the hash codes match.
Why is it bad? Two objects of equal value in two buckets?
Why is it bad if we have two objects of equal value in two different buckets? Well, that's not what a set's supposed to do. A set is supposed to only have unique items in it. And if we have two items that are equal, that are both in the set at the same time, then that is not allowed. It is considered a failure of the set itself.
What is well, why do we need to change the hash code to be based on value?
Why do we need to change the hash code to be based on value? Because if things are equal, then we do want to ensure that only one of them stays in the hash code at a time. And we want to make sure that that's the case because that's what a set is supposed to do.
Wait, but then couldn't we still just remove couldn't we still just check for couldn't we just still check for
Could we check for all the other bins for another equal value? Yeah, but then you kind of lose the point of the hash set, right?
Oh.
Right? If you do that, then now you need to check every other bin, and that takes linear time in the number of items. So we kind of lose constant time access if we do that. Yeah.
Yeah. So if you're taking the hash code by the original hash code function, why would there even be a possibility of assigning it to a different bin? Because when you do the module is on the number of bins, won't it be assigned to the same bin and like by default? Like why is there a case where
Well, if we use the default hash code, there is still a chance that it gets assigned different bins if the thing that the hash code's looking at differs, even though the equals doesn't check that. In this case here, equals was checking if two things have the same numeric value, whereas hash code was looking at different memory addresses. We can imagine that we have two different memory addresses that both contain 0. And those two are going to end up in different hash bins because their hash codes are different, because their memory addresses are different.
So like it was checking the equals method was checking the hash codes correctly, right? Isn't that like all
The equals method was not checking if the hash codes were the same.
even in the original implementation?
Yeah, it was checking if the number was the same, which is not the same as the hash code.
Oh.
Yeah.
Fix it by just
You could fix it by checking if the hash code's the same, but that also just means it's the default equals, right? Two things are considered equal only if they're at the same memory address. So it's not as useful. I do need to move on, sorry. You can talk to me after class. Sorry. Now, there's one other issue with a hash set that I want to go over, and that's what happens if things change internally. So we'll define an immutable data type as something which can't change in any way after you create it. So for an example, an integer, a string, those tend to be immutable because you need to create a new version of this every time you make a new thing. The integer class is actually immutable. It creates like a 5, and that 5 is unable to be changed from then on. Mutable things include things like the deck class or the percolation, because you can make changes to it as you go, right? If I add last to a deck, I've changed the deck somehow. Here's an example of a date class, which is guaranteed to never change. We use this final keyword, which prevents changes of values after you've set them. And the month, the day, the year are all unmodifiable because they're all set to final. Once you create it, it is stuck in that form directly. There's no way to change this. Do you have a question?
I'm just gonna say that's because that's the built-in date class, not one that we build ourselves.
No. Yeah, we can build this ourselves. It is possible to build this using this final keyword. The final keyword effectively prevents that object from changing. Now, final is neither sufficient nor necessary for a class to be immutable. We'll show a few examples here. So let's just take a quick look. Which of the following do you think are immutable? They are unable to be changed by code no matter how. Let's take a few minutes to discuss. So immutability means you're unable to change it whatsoever. There's no way to change things. All right, let's bring everyone back. All right, so let's start off with the first one. How many people think this is mutable? It is changeable by something. Everyone, how do you change it? Yeah.
Um, Whatever the name is, or pebble dot weight equals something.
Yeah. Pebble dot weight equals 2. You can do that. It is mutable. What about the second one? How many people think it's mutable? It's immutable? Yeah. No mutation is possible. Now, there is a way to change things if you use this reflections library, which lets you disobey these modifiers. Because in Java, if there is a will, there is a way. But we're not talking about that. We're going to assume it is immutable. How about this third one? Is it mutable? Few people say yes. How can we mutate this? Yeah.
What the rock list is, or like what it's pointing to, or that what that variable is pointing to, we can change that date. We can change that. We can change the list itself because that's a mutable data type.
Yeah. Even though we can't change the rocks array itself, we are able to change things inside that array. That doesn't change the pointer to the array. It just changes the items in there. So we are able to actually change a few things like this. Yeah, the final keyword only applies to the object itself, not to the things inside the object. How about this last one? How many people think this is immutable? This cannot be changed. Everyone? Or everyone? Feels iffy?
Like there's no method that can see to change it. So it's going to be an object with a pointer somewhere that there's no way to access where that pointer is. So it's never going to change. There's no way to change it. There's no way to access it either.
Yeah.
So you can't change. Like you can have a function, a method inside that says like append something to a rock. You just call that method. You never know.
Well, yes, if there was a method in here, maybe, but we don't see any methods. This is the entire class, let's say. Even then, it is actually still mutable. Here's kind of the crazy way you might do this. The idea is you create a rocks array, then you send that into the secret rocks box. That pointer is stuck. You can't access that. But you still have a second pointer to this same array from before, and you can use that pointer to make changes to this. So because of that, the secret rocks box is not immutable. It can be changed by external use. Once we lose this rocks pointer, it becomes immutable. But it is by default considered immutable because of this.
Wait, if an immutable object,
Go ahead.
if an immutable object has mutable members slash components, like can those be changed?
If a mutable object has mutable components, can those be changed?
Like if an immutable object has a
Well, immutable objects just can't have mutable components. If anything is mutable inside it, then it is immutable, guaranteed. Yeah. So out of these, only this second one is considered immutable. Now, in order to make things immutable, the only way we can fix this is by creating an entirely new array itself. This is going to work. So if we do an array copy, we are going to be able to create a separate pointer, and we no longer have that issue of two pointers pointing to the same thing. Now, the advantage of immutability is that you have less to think about. You can avoid bugs. It makes debugging a lot easier. And that actually saves a lot of time. The disadvantage is that creating a new object is going to be really slow. String concatenation is really slow because of this. Because that, sorry. Because strings are immutable, you need to create a new string every time you want to make a new, you want to add a new character. That's why string builders exist, for example. Now, in principle, we can put mutable items into sets. What's the possible downside with that? Yeah.
Change. So Like the set is infinity.
Yeah. Let's say that we have this array list, for example, right? And it's set to 0, 1. This is going to have a hash code of 962. If we add a new item, if we add this to a hash set, it'll be in bucket 2. But if we add a new item, let's say 7 in here, then now 017 is going to have a different hash code. And if 017 has a different hash code, we can't find that. It might be in a different bin. Because of that, if I decide to do this, then I can't actually find the item. Oops, this is the wrong one. Then I can't actually find the item. Item starts off as 0, 1 and it has hash code 962. But after I add the 7, it has hash code 29829. It can no longer find the item, even though the list is still in the hash code, in the hash set, because it ends up putting itself in the wrong bin. So because of that, contains is going to fail here because it looks in the wrong spot. The bottom line here is that you should never mutate an object being used as a key. If you do, then it's going to change its hash code potentially, and it is going to put itself in the wrong spot. Now, you can, in theory, keep mutations if the mutation doesn't affect the things that hash code changes. The official wording in the Java documents is that you're allowed to change things as long as it doesn't affect the equals operator. Java's hash code is designed to be working with equals and only equals. So there's a lot of references to equals in there. Any questions up to here? All right. Now, that's most of what we want to cover today. But before we finish off, I want to kind of look at the actual hash set in Java. If you look at the actual code for Java's hash set, which you can in here, it is fully in GitHub. You might realize that hash set is just a hash map. It is a hash map that just sets everything to the values to null. Why reinvent the wheel if you don't have to? When it does actually use hash map, an interesting thing is it basically does what we're saying, but it does this kind of weird reduce function that's slightly different. You don't have to worry about its difference. You can talk to me at office hours if you want to discuss further. The other big thing is that hash table starts at size 16, doubles every time the load factor defaults exceeds 0.75. So we can actually simulate this with our hash table visualizer. I can set the number of starting bins to this, and I can set the resize factor to 0.75, and I can add a ton of items. How many items do you want to add? 1,000? Let's add 1,000 items to this, and we'll see that it effectively leaves everything roughly. I picked the wrong thing, didn't I? Yeah. Oops, this is the 0, 1. Sorry. How do I set this up? This thing, and then color hash table visualizer. I set this back to I. If I do this, yeah, it starts off by, it's using color. Right. Return num. There it is. Let's see. All right. It adds everything. Everything's nice and even. Ish. Yeah. The same is true even if I set up the hash table visualizer to use random numbers. If I do this, then yeah, you can see that roughly everything is fixed by constant amount, and that's effectively what we're going to be targeting. Now,
I have one question.
Yeah.
Have you heard of the previous please?
Yeah, sure.
One before. I'll just